Alright guys, welcome to another video of GGTutoring, and today I'll be focusing on Chem 343 organic chemistry, specifically on the first two main reactions of chapter 5 that we learned so far. I'm going to cover the HX edition from the first unit we did, but I'm also going to mainly be covering the X2 editions of bromine, specifically halogenation and a halohydride formation. Okay? The reason why I include the HX edition from the first unit is to kind of like give some background knowledge and to help explain further the mechanisms of halogenation, halohydride formation, and why we do these different mechanisms and reactions, okay? So I'm going to start by explaining and walking through the process of HX addition. If you guys already know this, you guys can feel free to skip forward till when I talk about the halogenation halohydride. So some key things to know about the HX addition is that there is Markovnikov regiochemistry, which basically means that the more substituted carbon will take the bromine, the least substituted carbon will take the hydrogen. We already know this from Unit 1. And there's going to be a mixture of anti or syn products, which I'll describe more as I draw the products. And there can be rearrangements in formation of carbocations. So like let's say like you have like a 2' carbocation, but you could see that you could do a methide shift or a hydride shift. These are possible in the HX addition to make a more stable product. Okay, so I'm going to start off through it with the HX addition now. So we know we have our HBr, so I'm going to draw that in. I'm going to add all the lone pairs just for simplicity and so everyone can follow. And we're going to do the obvious electron push mechanisms to know where everything is going. So with our double bond, I'm going to change the color. We know that the double bond is going to come in and take the hydrogen. And it's going to break off the bromine, right? So now we're going to draw the new intermediate where we have boom. And we know that the hydrogen is going to add to the least stable cation, which would be would add to this one right here, this carbon. And then we know that this will become our cation, which is a positive. And we know that this carbocation is actually a 3' carbocation, so we can just mark that. So we have the bromine ion just floating around in space with the negative charge. To keep formal charges there, so it's simple. So we know that there's a positive charge on this carbocation, so we can take the lone pairs from the bromine and they can add to that carbocation. And now we can draw our final product, right? So we'll get the same ring structure, obviously. And we'll get a mixture of products. So either our bromine can be on a dash, like so, or it can be on a, it could either be on a wedge, or it can be on a wedge, or it can be on a dash. I'm sorry, guys. You get the point. So basically, it doesn't really matter because this CH group, methyl group, it can just change positions. Doesn't really matter too much, and this is why we can get anti or syn products. And that's basically the end of this reaction. It's pretty straightforward, pretty simple reaction. You know, you want to form the most stable product, and luckily we didn't have to do any rearrangements or any hydride shifts or methyl shifts. But now, for the more complex mechanisms, the X2 addition, specifically halogenation, there are no rearrangements, which means there are no carbocations. So this mechanism does not go through a carbocation. And one thing to note is that it says anti-only stereochemistry. The products are only anti, which I'll explain more. And it still follows Markovnikov regiochemistry, where the bromines will want to add to the more substituted carbon in the double bond, but I'll explain as we continue. So normally for this reaction, this can occur as I drew the arrow with the bromine on top, and on the bottom it's a CH2Cl2, or it can occur in CCl4, which is basically just different solvents for this to occur. Basically, just recognize that if you see a Br2 and underneath the arrow you see a CH2Cl2 or a CCl4, you know this is probably going to be halogenation, right? So I'm going to draw the bromine molecule. I'm going to redraw it though, not on the arrow, with its lone pairs. And for the double bond that's going to attach to this bromine, one of them is going to have a partial positive charge, and one is going to have a partial negative charge because there's a lot of electron density within the pi bond itself, which is going to attract one of the bromines. So in this mechanism, the electrons from the pi bond is going to come to the bromine, but unlike the HBr reactions where it's a little different, one of the lone pairs on the bromine is going to come back to like one of the carbons on that pi bond and form a ring structure. It's gonna attach as a ring. And then when this happens, one of the bromines is going to get knocked off. So our intermediate that forms is going to be as shown. We're going to get something that looks like this. You're going to have two lone pairs on this bromine, and it's going to be a positive charge. And then we can draw this like so, with our hydrogens coming out like this. Doesn't really matter but how you draw it, but as long as you get this cyclic ring structure, that's really important. And you'll still have a bromine ion floating around, right? Now, this bromine ion, since the bromine originally that we took over here, as I'm zooming in, this bromine, I'll just circle it. This bromine that added to the pi bond, it added cis to the double bond. So it added to the same plane because there's two bonds. You can't have one bond coming off in a wedge, one off in a dash. It has to be within the same plane. But the new bromine ion has to add anti to the pi bond, to the other bromine atom, because this is how this reaction mechanism works. And we also know that since these two carbons attached to the bromine, they're both going to be partial positives, but you want to add to the carbocation that is more stabilized because it can better hold a positive charge. In this case, the carbons that the bromine is attached to are both the same carbocation. One is not more stable than the other, so it doesn't really matter where you add from, but there will be two different mixtures of products. So this bromine ion that's floating around in space is going to add anti, so it's going to come all the way around and add from the back side to that carbon, and it's going to break off this bond and leave a bromine. So I'll draw the new formation of this product, and we're going to get something that looks like we're going to have our bromine like so, but now it's going to have three lone pairs because one of the bonds broke and added the bonds of the bond went to the bromine. You're still going to have your your hydrogens coming off in the dash and wedge. But now, since it added anti, this bromine ion, it's going to form like this because it's away from its opposite of the bromine. And you're going to get a dash wedge of your hydrogens. And this is what one of your products will look like. And also recognize that it can add from any side. So also this bromine could come around and add like this and break off this bond. So you'd also get a product that would look something like, let me redraw. It would look something like this. It's kind of important to know this because the stereochemistries might difference. If you watched my last video about assigning R and S configurations, this does come into play when trying to figure out if they're enantiomers, diastomers, or meso compounds. We can make more videos in the future explaining those, but for the simplicity of this video, just know that there are different ways that the bromine could add, and it is important to know the different products that it can make. But basically, this is what you're going to get. The reason for doing this than not doing what we would normally do, like in the HBr reaction, where you would just have a carbocation, this can be more controlled, and it can give rise to different products, which is basically the goal. Because you don't always want to do this HX addition where you need to form a carbocation. So maybe for different reaction mechanisms, if you're like a scientist trying to do something else, you might want to do halogenation. So it's kind of important to know how to do this and the mechanism behind it. But similarly, we're going to do the same X2 addition, but we're going to do it for a halohydrin. Basically, I'm doing the exact same molecule. We're going to have the Br2, but the thing that's different is that there's the H2O molecule right here, instead of the CH2Cl2 or the CCl4 as mentioned before. So this kind of changes the nucleophile after you add the first bromine. So it's going to proceed the same way. You have your bromine, your Br2, it has its lone pairs, and as again, like I said before, one of them is going to be a partial positive, One's going to be a partial negative because of the electron density within the pi bond. And we know that the electron density, it's going to come and grab this Br, and then one of the lone pairs is going to go back to the carbon. And it's going to make that ring structure, as I said before. So we're going to get something that looks like this. We're going to have our Br. It's going to have two lone pairs and a plus formal positive charge. And we still have our, dash and wedge hydrogens coming out on both sides. But this time, like before, you'd assume that the bromine ion that's not floating in space, I'll redraw it, would come and attach anti on the other side of the double bond and, have an anti-product addition, right? But because our solvent is water now, there's actually a bunch of water molecules that are just like, the bromine's just, it's dissolved in water, right? So there's a bunch of water molecules that are just surrounding this bromine ion, right? Looking like this. There's millions and millions of water molecules in solution, right? But your bromine ions look something like this. And we know that our actually our hydrogens are positive charged as compared to our oxygen, because oxygen is more like electronegative. So the hydrogen and the water molecules are basically gonna trap this bromine ion, and it can't really add to this molecule now. So now our water is actually going to be it's going to be our stronger nucleophile, and now water instead of bromine is going to add anti. It's the exact same mechanism, but now we're using water. So basically, I'm only going to draw one of the products because I've already drawn above that we can do either way to either carbon, because they're the exact same carbon in terms of stability, because we both know that these are both partial positives, but they're equal in carrying the positive charge because one's not more substituted. So this water molecule is going to come around, and it's going to add to this carbon, and it's going to break off that bond, right? So now I'll draw our new product. I'll draw an arrow. And as we know, the bond is going to break. So we're going to have a bromine like this. We're going to have, sorry guys, we're going to have our normal thing. We're going to have our water. We're going to have our water that attached. It's going to have a lone pair. It's going to have two hydrogens. It's going to have a positive charge on it. And we'll have our implicit hydrogens, which I'll draw. You don't really need to worry about them because they're there. But we can draw them for keepsake, just to keep track of them. Our implicit hydrogens are going to be drawn as shown. But because this water is a solvent as water, there's millions of water molecules. So we can take more water molecules to stabilize this that I've drawn up here, because it has a positive charge. So we can have more water molecules, and it's just going to come and grab one of these hydrogens and take it to the oxygen. And you're going to get a final product that looks something like, you're going to have an OH group. It has two lone pairs, and you get all your formal lone pairs. And you're going to get a product that looks just like this. And that's how you kind of complete this reaction, guys. It's really simple. You just need to memorize. You need to also realize that, similar to the halogenation, it still has Markovnikov regiochemistry. It has anti-only products, and there is no carbocation, and there's no rearrangement, which is the way of kind of controlling this mechanism and getting desired products that you might want. So it's very similar to halogenation, but instead we're using water. You still have to stabilize it, and that's how you end up with OH, and you get a Br still. So I hope I explained this video very simple, I hope. If you guys have any concerns or questions, please leave a comment down below asking. I can try and explain further. And I hope you guys enjoyed this video. Thank you guys so much. Thank you for tuning in to GGTutoring, and I hope to see you guys in the next episode. Bye.